Like, no, this is all like grown up now. Okay, you just have to be prepared for that test. So, okay, we're done? This one? All right, so now we define something. We define what's called the gradient vector. This gradient vector is going to become very important to us as we proceed through this, this chapter, and we'll see it again later on too. This is supposed to be a dot product. I don't know why that looks like that, but remember that this is the definition of the directional derivative, which is what I wrote up there on the board. If I were to create two vectors, a vector that the first component was the partial of f with respect to x, and the second component was this, and I dot that with the vector AB, then wouldn't this be equal to this formula right here? Because when you dot product, don't you do this times this plus this times this? Isn't that what you do when you do a dot product? I know it's been a while since we did dot products, but dot product was easier than cross product. So this right here is another way of writing the directional derivative, isn't it? And so this right here, we knew that this was the directional derivative, right? That was directional vector. That was the vector that told us which way to point, right? This we've never really seen before. We've never actually put the partials together into a vector, have we? Never. But now we are. We're going to put the two partials into a vector, and that vector is called the gradient vector. This right here is called the gradient vector. But this note is just to make you aware of the fact that you could rewrite this formula as a dot product. The next note is where we define the gradient vector. So the gradient vector is defined as follows, and that's what I wrote right here. This is, you've seen the delta before, right? Delta x, change in x, right? You've seen that before. Flip that delta over. That's the symbol we use for the for the gradient. And it's actually, this symbol is called del, okay? It's called del, which is also what I told you this symbol is called for the partial derivative. So same name for two different symbols. It's confusing, I understand. So del f, you'll hear me say del f, and that's what I'm referring to, all right? So just remember that the gradient vector is exactly that. It is a vector, and it's just made up of partial derivatives. That's all it is. Gradient vector is just a vector with the components being partial derivatives. So simple example, find the gradient vector. So this is one of those problems like someone who's never even ever seen calculus 3 or anything like that or any of this vector, they look at that, they're like, man, that looks hard. What's a gradient vector? It's nothing. It's really not much. It's just a couple of partial derivatives, right? Well, you know what I'm saying? It's not like, this is not going to be a 3-page problem. This is just an exercise in partial derivatives. That's all it is. So the gradient vector is this, right? And so let's just compute what's the partial of f with respect to x. Let's see. So what is we have a sum, right? So we can do partial of e to the x y with respect to x would be y e to the x y. See, I'm assuming that you're okay with that by now, all right? That you can do partial derivatives by now. Plus derivative cosine of x plus y. What's the partial of that with respect to x? Negative sine x plus y. Anything else there? That's it. Okay, I agree. And then now we do comma. So the second component of the gradient vector is the partial of that with respect to y. So it's instead of y e to the xy, it's x e to the xy. And then minus, this part's exactly the same. Okay, so if you are still at a point right now where this is like, what the heck's going on? Well, you've got work to do this weekend then. I think the take-home that I gave you, the partials get a little complicated because there's some product rule in there that you have to keep track of, and That's it. That's the gradient vector. Congratulations. All right. Now we're going to see the gradient vector is extremely important. We're going to see its value in a little while, but before we get to why it's so important, let's extend everything now. You know, everything we've been doing so far, it's been f is a function of two variables, x and y. And so we were looking at it as a surface. The domain was down on the ground, right, in two-dimensional space. But hey, what about if we have a function of three variables, f of x, y, z? Now your domain lives where? Where's your domain? The domain's in R3, right? Let's say someone gives you a unit vector in R3, which would be a direction to point in three-dimensional space. Then the directional derivative, does this look familiar? This is exactly the formula before. I'm missing something. Do y'all see it? I'm missing all my z's. That's what happens when you copy paste. Hey, it was my own work. Prove it, yeah. Okay, so the only difference between this and the one I put up on the board here is that because we have three variables, we're going to have three pieces, right? Three partials, partial with respect to x, y, and z. Each of these functions can be evaluated at an ordered triple x, y, z. And we'll have a, b, and then a third component of the unit vector. So everything straightforward, yeah? And then you could also break this apart as a dot product again. And we could call the partial of f with respect to x, partial of f with respect to y, partial of f with respect to z, put that into a vector, and we would call that the gradient vector for this function. So there's two different notations. Del f is either write it out that way with all the x, y, z's, that's too much, or just shorthand is something like that. Now this is something in the homework video I did this morning. I was trying to get this across in one of the examples, but you know, I think I just made it clear. Hopefully it made sense that, you know, the problem that we started with, we had a point in the domain. We pointed out, the first one we did, we pointed pi over 6, right? Then we went up on the surface, and here was the ground, and we were pointing out this direction, and we had some point out here, and we were trying to point parallel to it, right? And we got, you know, if we walked out, what happened? You know, we went up or down, right? That's what's happening when you have a function of two variables. But what if you have a function of three? Well, your domain is no longer this picture, right? Your domain actually is three-dimensional. The point that you pick instead of being like this is, you know, some point in three-dimensional space. And the vector, the unit vector that you're pointing in, is actually a three-dimensional vector here, right? And so this point gets plugged into a function. I don't get to see that function. I can't visualize it. So it can't be me standing on a surface anymore. It's something else. So one of the clearest examples I can think of is imagine that this point lives in this room, right? And that's the temperature, right? And that's the one we keep going to, right? So then if I'm this point and I go start moving in a direction parallel to this red vector, so I start moving parallel, then what I want to know is as I move, how much does the temperature increase by? So the temperature is the output of this function. And so that would give me my instantaneous rate of change in temperature. Now I've been trying to put together a demonstration of this, a way to visualize a function like this, and I've almost got it done. What I've got is a point that's moving around in three-dimensional space that you can move, but I can't do temperature, right? So what it is right now is it's a green dot. And as you move around, it changes intensity. So it goes from like dark green to really light, like bright green. And so as you move around in space, like the function dictates the brightness of the dot. So the brightness of the dot's that output. It's a work in progress. I don't like what I have so far. So, okay, so what I'm getting at is with this, you cannot be talking about standing on a surface. Okay, we can only do that when the function is two variables. Can we actually visualize that? Why don't you work on this? See how long it takes you to get through this. You can talk to each other, all right? This is not a quiz or anything. I just want to see what you do here. Can everyone read it? I'll make it a little bigger. So, that okay? Okay. Find the gradient vector. Then do the directional derivative at this point in that direction. Go ahead. I'll give you like 10 seconds? 10 minutes? 10 minutes. Progress or no?
Yes.
Yes? Got progress? All right. Let's see here. Anybody want to volunteer the gradient vector for me? Anybody feel good about their gradient vector?
I do, but I don't want to put myself out there.
Oh, come on. You can always just put or something if you want. Come on, go for it. I mean,
1 over y plus z
1 over y plus z.
and negative x over y plus z squared,
Y plus z
all of it squared.
squared.
And then the same thing.
Negative x again.
Yeah, negative x over y plus z squared.
Or y plus z squared. Okay, anybody agree? Got 1 agreeer, 2 agreeers,
I agree.
3, 4. We got 4 people who agree.
Yourself.
Come on, guys, I thought we were friends. Is this how it's going to be? Okay.
So should I go through these, or I don't mind. You just got to let me know. Yes.
X in the first component.
Should be z. Yeah, thank you. This should be z. Thank you. I don't know if you probably said z. I just or something.
It's no big.
Okay, so we agree with this now?
Yeah.
All right, so the first one is the easiest because you really have 1 over y plus z times x, right? On the first, like on this, right? That's what this is. And if I take derivative of that with respect to x, y and z are constants. That means this is a constant. Constant times x, derivative is just a constant. So that's this, right? Yeah? Now, if I want to take the partial of this with respect to y, x is a constant, so it's going to come along for the ride. So forget about that for now. But to do the derivative of this, because y appears in the denominator, you probably should move the y plus z up to the numerator, like that, and then take the derivative of this, which is chain rule. So negative 1 comes out, y plus z to the negative 2 times the derivative of what's inside with respect to y, which is 1 plus 0, because z is a constant. So just a 1 out here. But that's same as negative 1 over y plus z squared, right? But then you had the x. So x on top, so that's this. And then the other one with respect to z works exactly the same way. We good? Yeah? Okay. That's the gradient vector. Now what we need is the directional derivative at the point 411 in the direction of u. Did anyone get that part yet? So what did you do?
On the unit vector.
So you looked at the u and had to make sure it was a unit vector, which it wasn't, right? So you looked at u and realized it wasn't a unit vector, so you found its length. Square root of 1 plus 4 plus 9, which is root 14. And so I'm going to scale each of these components by this. I'll call that vector v is equal to 1 over root 14, 2 over root 14, 3 over root 14. And now it's just the formula, right? This is my a, b, and c. And so I'm going to take this vector and dot it with this vector, right? Take the v and dot it with this. So let's do that right here. What's the gradient dotted with v? It is 1 over root 14 times this plus 2 over root 14 times this plus 3 over root 14 times this, which gives us 1 over root 14 times 1 plus y, 1 over y plus z. And then this is going to be negative because that was minus 2 over root 14 times x over y plus z squared, and then finally minus 3 over root 14 times x over y plus z squared. And that's a number, isn't it? Dot products spit out numbers, don't they? Well, I have to give you x, y, and z, and then it'll spit a number out. But all right, so let's go ahead and I don't think I'm going to go through and plug everything in. Someone can tell me what the directional derivative in the direction of v of the function is at the point 4, 1, 1. What do you get? Negative 1.2. Anybody have the exact form, or is it real ugly?
Oh, it's negative 9 over 2.
It's negative 9 over 2 root 14. Anyone else get that? Yes? Okay, so all we do is replace x with 4, y with 1, z with 1 into this, and you should get this, which turns into this if we get on our calculator. So again, let's say that this function right here represented temperature in the room, and you're at the point 411, wherever that is, and you start moving in the direction of this vector, and you start moving that way, the temperature is actually decreasing at that rate, negative 1.2 degrees. All right. All right, we're moving on. This is the most profound part of the entire class, this part right here. And this is the most important thing about the gradient vector up to this point. Is that if you were, go back, let's go to the surface because it's the easiest thing. You're standing on the surface, right? And you are up at some point, and you know that in each direction, right? In each direction, there's going to be some tangent line. The natural question would be, what direction do I point in to have the steepest tangent line, right? Like, where should I point so that when I take that step, I go up more than I would in any other direction? Does that seem like a very difficult question to answer? Yes or no? Does it seem like if you know the function that it's going to be easy or hard to be able to tell where to point and walk and that be the steepest? I mean, to me, that seems like a stretch. Like, we probably have to work pretty hard to get that information. But it turns out it's not hard at all. And it comes from the fact that we have a dot product. All right? So you go and you look at this. We are trying to figure out what will maximize the directional derivative. What will give us the largest directional derivative? Well, if we look at back from dot product, way, way back when, the definition of the dot product, we had this alternative definition, right? Where as long as these weren't zero vectors, the dot product is equal to the magnitude of u times the magnitude of v times cosine of theta, where theta is the angle between the two vectors, right? And if we know that the directional derivative can be rewritten as a dot product, then we know that the directional derivative can also be transformed into this formula right here. Right? That's the directional derivative. Using the dot product formula, this is magnitude of f times magnitude of u cosine of theta. Right? Y is the next step here. U is a unit vector, right? So the magnitude of u should be 1. Yeah? So this formula turns into this. So the question now is, what will make this the biggest it can ever be? If this number right here is 1, right? Because cosine, the biggest it can be is 1. And the way that you get cosine to be 1 is by letting the angle be 0, right? Yes? That means that the angle, to get the biggest possible directional derivative, the angle between your gradient vector and the direction that you're pointing must be 0. So think about that. This is the profound statement. I'm up here and I'm like, okay, which way do I point? Which way do I point? Okay, let's call this u. That's the direction that I'm trying to point, right? And then I've got this gradient vector, which seems to have nothing to do with this, right? The gradient vector is the partial derivatives. and then someone's telling me to point in a direction. I'm saying, which way do I point so that I get steepest thing? Well, it turns out to get the steepest, you need the angle between these two vectors to be what? 0, which means that you must be pointing in the direction of the gradient. So the gradient vector itself is the direction that you should point to get your steepest descent. And that, to me, is amazing, all right? Because that means if you can calculate the gradient, then you know which way to point to get steepest descent. So this is the summary of it right here. Maximize the directional derivative. The maximum value of the directional derivative, the maximum value, is the magnitude of the gradient. The length of the gradient vector is the steepest slope you're ever going to have. And it occurs when we point in the direction of the gradient. Remember that. That's a big note right there. So here's an example. We have this function of two variables. First, let's find the direction as an angle of the maximum rate of change at 0, 0. So you've got some surface sitting up here, floating around here. It's not really floating. And you're at the origin, right? 0, 0. You go up to the function. Somewhere on the function, you're standing there. And I'm asking you, which way do you point? Tell me which way you point so that you would get the maximum directional derivative. What do I have to do? I just have to find the gradient. That's all I have to do. Okay? So what's the gradient of f? Well, it's partial of that with respect to x, which is cosine x minus y minus sine x, right? So you have to do derivative of each of those, right? So derivative of sine of x minus y is cosine of x minus y. Derivative of the inside of this is just 1, plus the derivative of cosine x, which is negative sine x. So that gives you this. Then that's your partial with respect to x. Partial with respect to y is, be a little careful here, cosine of x minus y, but then derivative inside is what? Negative 1. So it's negative cosine of x minus y. And then derivative of this piece, 0, because x is a constant. So that's it, right? That's my gradient vector. All I need to do now is plug the point in. If I take the point 0, 0 into that, that will be the direction I should point, right? Because this is a vector. The vector gives me a direction. So cosine of 0 is 1. Sine of 0, 0, so there. Cosine of 0 is 1, but then negative, so negative 1. That's it right there. That's the direction I should point, right? So this goes back to like that domain picture. We were sitting here, we were at 0, 0, and then normally, like what I had given you in the past, I told you what direction to point, right? I gave that to you. This question is asking which direction do I point for steepest descent or steepest rate of change. It's telling me to point here. So I point 1, negative 1, 1, negative 1. I point that way, and that's going to give me the steepest descent. I wanted it, though, as an angle, not as a vector. So what is that as an angle? So to answer this question, what is it? You say negative as an angle, not the point that you're at. Relative to the x-axis, right? That's the angle I should point. If I want to have the steepest ascent, what I need to do, standing at 0, 0, is I need to point negative 45 degrees, pi over 4. You could make it relative to the y-axis, but then everyone would be like, why? Everything's always been relative to the x-axis, But you could. Just make sure you state it. That way there's no confusion. We good? That answers part A. What about part B? Find the maximum rate of change. So what is that maximum rate of change? It's the magnitude of that derivative. So all you have to do is take the magnitude of this. Square root 2? Root 2. Come on, this has got to be somewhat amazing. No, only to me, I guess. Only to me. You've got this surface, you're standing on it, you're trying to figure out where to go, that you have the steepest descent. I can tell you which way to point, and I can tell you that's the steepest descent you're ever going to get. Root 2, that's it. You point in any other direction, it's going to be less. And it didn't take a whole lot of work for me to be able to tell you that. And then what I could do is I could move in that direction, right? I start moving in that direction, and I say the same thing at the next point I get to. And that would give me another direction, wouldn't it? And I keep doing that as I move, and eventually I'd be at the top, wouldn't I? And that's where you have